Welcome to the class, student. Today we will do optical isomerism. Last time you people have seen optical activity. Organic compounds are classified as on the basis of how they rotate the plane of the polarized light, whether clockwise or anti-clockwise. If they rotate clockwise, that is your in the right side, then they are called dextrorotatory, and if they are moving the plane of the polarized light to the anti-clockwise direction, that is left hand side, then they are called levorotatory. So now I will teach you the conditions how you will find out that whether a given compound is optically active or not. Okay, so conditions for a compound to be optically active. So the first condition is it is organic compound, no doubt. This is organic compound. So first one there, that is presence of a chiral carbon. I am not saying a chiral. If you say a chiral, meaning will be different. I am saying a chiral or asymmetric or dissymmetric carbon atom. So either you say chiral or asymmetric or dissymmetric, meaning is same. So what is a chiral? What is a chiral carbon atom, or what is the asymmetric or dissymmetric carbon atom? Carbon valency is 4, you know, and this 4 valency is tetrahedral. We have done earlier. This is your tetrahedral. This is the tetrahedral shape. So if all the 4 valencies are satisfied by 4 different atoms or group of atoms, when 4 valencies of carbon atom is satisfied by 4 different atoms or group of atoms, then the carbon is called a chiral carbon, and we mark this carbon with an asterisk. Asterisk means this sign. This is. So here this carbon is having 4 different atom or group of atoms. So this carbon is chiral. So you will mark it with a asterisk. So this sign is indicating that this carbon is a chiral carbon. See one example of this. This is here carbon, a functional group COOH, another functional group CH3, another functional group OH and H. Atom, group of atoms. So this carbon is chiral carbon. This is your lactic acid. Okay, so take one more example. If you have this compound COOH, COOH, CHOH, COH, H. Now, if you see this carbon, all the four valency 1, 2, 3, 4. This is different. This is different. This is different, and this valency by this whole group different. So this carbon is a chiral carbon. Similarly, for this carbon, this is different. This is different. This is different, and for this whole, this is. So this carbon is also a chiral. So this carbon has got, this compound has got two chiral carbon. This is example of tartaric acid. These both examples are especially mentioned in your syllabus. So this is the first point that you have to do for condition. So first condition is you have to look for the chiral carbon atom. But student, here you remember that it is not necessary that a compound which has a chiral carbon or an asymmetric carbon will be surely optically active. It may be or may not be. So this is first point, and second point has to be followed. So the compound which is which is having a chiral carbon, it should have the second property what? That is, its two isomer. Optically active compound will have two isomer. One that is will have your what? Clockwise rotation, the other will have anti-clockwise rotation. So the two compounds, if I take two compounds A, B, C and D, then if this is showing rotation, say I take the rotation clockwise. This is clockwise rotation if it is showing clockwise rotation. So this is your called dextro rotatory and symbolized by small d or with a plus sign. Then another isomer of this will be showing rotation anti-clockwise and is called levorotatory and is symbolized by small l or with a minus sign. So these two forms, they should have relationship of a plane mirror in object and its plane mirror image. If one isomer is behaving like object, then the other isomer should be its mirror image, plane mirror image. So if this is your mirror, then this should be the plane mirror image. So how it will be? You know, in plane mirror, closer things are seen closer and farther things are seen farther. So A will be there. See, I am not talking about later inversions. So I am not showing this will be like this. So that is not my aim. So here we'll have this B closer. This is also closer. So C will be this side. This is farther, so D. You can see here, this will be. It won't be like this. It won't be like this because this is closer to this. So same distance, equal distance here. So that is your C. Okay. So this is a chiral carbon and this is also a chiral carbon. First condition is there, and here it is your from D to B and here from D to B. So this is clockwise, anti-clockwise. So two isomers, dextro and levo form. They should have second point is what? They should have relationship of object and its plane mirror image. The two isomers have this have relationship. So they should have relationship of object. They should have, or I rewrite it clearly for you here. The two optical isomers must have a relationship of object and its plane mirror image. This is second point. And when two isomers have this relationship, then the two isomers are called the two isomers which have object and its plane mirror image relationship are called enantiomers. They are called enantiomers. Very important. So the second point is the two isomers should be enantiomers. Enantiomers means they are having relationship of object and its plane mirror image. So these two are your what? These two are enantiomers. So now I give you the example for this, and I show you also how to draw. So take example lactic acid. Lactic acid sometimes in examination is given like this. Like this. So you will have to make yourself the structure. So you will choose the central carbon. To this carbon we have this group attached. To this carbon we have H attached and OH attached. And to this carbon we have CH3 also attached. So one side COOH. So this is the structure. So which group to be draw where, that you have to. So first you will draw separately this group. So here I write the structure for you. So we have got one group this, we have got one hydrogen, one we have got OH, and then one we have got CH3, one we have got this. So this carbon is chiral. Now which group to write where, you first find out which is the heaviest among all. So calculate molecular weight. So here carbon 12, oxygen 16, here 16 plus 1. So it will be 45. 45, and here we have for hydrogen 1, for OH we have 16 plus 1 is equal to 17, and for this we have 12 plus 3 is equal to 15. So you have found out their molecular weight. Now you will keep this group in the increasing order of their bulkiness, increasing order of their mass. clockwise. So bulkiest should be always at the top. It's not a hard and fast rule, but it is convenient if you follow. Then next we have 17, that is OH. So OH will be clockwise. Then next is CH3 and the lightest is H. So we have arranged them like this. Then mirror image we will draw, as I told you, closer things closer. So here it will be COH. Inversion we are not aiming at, later inversion, so that is, and OH here and CH3 here and H here. So we have got two isomer, and now you have to show which is your dextro and which is levo. So if you draw this way, as I told you, increasing order of their molecular weight, you arrange clockwise, then very easily you can decide which is dextro, which is levo. So you will see only left side and right hand side. Left side lighter, this side is heavier. So you will show the movement of the light from the lighter group towards the bulkier group. So this you are getting clockwise. So this is D. This is lactic acid. So you will say D lactic acid or plus lactic acid. This is dextro rotatory. In this case, lighter to bulkier, and so this is L lactic acid, levorotatory lactic acid minus lactic. So this was the second point, and you could do it. Now the third point. The third point is the enantiomers. What is the meaning of enantiomers? The two isomers, dextro and levo forms, they have relationship of object and plane mirror image. So the two forms, they are called enantiomers. They should, third point, not the enantiomers must be non-superimposable. They should be, enantiomers should be non-superimposable. Means what? If you pick up this molecule and place at the top of this. So if you pick up this and place at the top of this, then what will happen? COH will be overlapped by COH. This carbon will be overlapped by this carbon. Fine. But if you place this here, above H will be OH, but CH3 will not be over CH3. CH3 will be here, and above OH will come H. So this is called, they are not, the similar groups are not overlapping, and that is called non-superimposability. So these two isomers, they should be non-superimposable. So the first point is what? They should have asymmetric carbon, chiral carbon. Second point is the two isomer, optical isomer, dextro and levo form, they should be enantiomers. Enantiomers means they should be having a relationship of object and its plane mirror image. So these two forms are called enantiomers. Therefore, optical isomerism is also called enantiomerism. Optical isomerism is also called enantiomerism because these two forms are your enantiomers. Or these two forms are also called enantiomorphs. They are also called enantiomorphs. So the optical isomerism is also called enantiomorphism. So optical isomerism you say, or enantiomerism you say, or enantiomorphism you say. Okay, optical isomer or enantiomers or enantiomorphs. So these are the names you should know. So you have seen that non-superimposability, and non-superimposability means dextroform and levoform, if they are placed at the top of the other, one form is placed at the top of the other, similar group will not overlap. Even if you rotate them by 180 degree, if you rotate this group by, you place it here and then rotate by 180, what will happen? This will come here, that will go there, and still on rotation at 180, they are not going to overlap, so they will remain non-superimposable. So here this is about your this thing, optical isomerism. Now I'll teach you the racemic mixture. The next point is next thing you have to do, racemic mixture. So racemic mixture. What is racemic mixture? Equimolecular. Very important. Equimolecular mixture. I am saying mixture. Mixture means having no fixed formula. Equimolecular mixture of D and L forms of optical isomers is called racemic mixture. So if you remember the phenomena I taught you, that polarimeter tube, and here you have the plane polarized light which you have received. When the plane light passed through, or I draw here, this was your ordinary light which is vibrating in all the direction. When this light is passed through Nicol prism, which is called polarizer, the plane polarized light is formed. That is its vibration. The light will be set in one direction perpendicular to the plane of the propagation of light, and this is polarimeter tube. And in this you fill the organic compound whose optical activity has to be known, and then you will have here the observation. So when we fill here a racemic mixture means equimolecular. If 10 molecules of D form and 10 molecules of L form, that is the meaning. If you feed here your racemic mixture, then what do you see? That the plane of the polarized light is remaining the same. It is neither moving to the clockwise nor moving to the anti-clockwise. So this racemic mixture is optically inactive because the plane of the polarized light is not rotating to any direction, neither to clockwise nor to anti-clockwise. So this form, racemic mixture, is symbolized by DL form. If you say DL form, it means racemic mixture or plus minus form. Both dextro levo are there. So why it is so? If you have this compound lactic acid and this is D form, and this is your L form. One molecule if you have put. So this will rotate the plane of the polarized light clockwise. This will rotate the plane of the polarized light anti-clockwise. So what will happen? The plane of the polarized light which is rotated by this to the clockwise direction, that will be cancelled by this. So the rotation of the plane of the polarized light is cancelled. So why this is optically inactive? Because plane of the polarized light is not rotated due to mutual cancellation. Mutual cancellation of rotation. Due to mutual cancellation of rotation, because of external compensation. One molecule, as I showed you, is rotating this side, other is that side. So externally they are compensating and causing cancellation of the rotation. So on this basis, lactic acid has 3 optical isomers. Number 1, D-lactic acid. Number 2, L-lactic acid. And number 3, D-L-lactic acid. D-lactic acid is optically active. Optically active. This is optically active, L. But DL form is optically inactive. It is optically inactive due to mutual cancellation of rotation because of external compensation. Now one more example we will do. That is tartaric acid mentioned in your syllabus. So if I do for tartaric acid, this is your 1, 2, 3 and 4. This is your tartaric acid. Same rule you have to follow. Around this, bulkier this and this and that. This is chiral. Then you will draw its mirror image. 1, 2, 3 and 4. So here will be OOH, OH, H, H, OH. And this is chiral. This is chiral. So if you see in this case, this around this lighter to bulkier, and here again lighter to bulkier. So around this carbon clockwise, around this carbon also clockwise. So this is D tartaric acid, dextro tartaric acid or plus tartric acid. In this case, lighter to bulkier, anti-clockwise around this carbon and this carbon. So this is L tartric acid, or minus tartric acid. So they are enantiomers. Now if you take equimolecular mixture of this and feed in your polarimeter tube, we will get one DL form, that is DL form, and this DL form, that will not be optically active. This is optically active, this is optically active, you can see, but here this is not optically active. So here DL form, why this is not optically active? That rotation caused by one form, one D form, will be cancelled by the rotation caused by L form due to external compensation. So DL form is optically inactive. In case of tartric acid, one more form is found, that is also optical isomer, because it has chiral carbon, COOH, OH, OH, OOH, H and H. This is chiral, this is chiral. In this case, you can see both OH groups are on the same side. In these, OH groups are on the opposite side. This form is called mesotartric acid. Mesotartric acid, in this case, if you see, and if you imagine here a mirror, so you can see that this half is a waving like object and this is mirror image, or you can say this will rotate the plane of the polarized light. If you see, lighter to bulkier, and here lighter to bulkier. So half molecule is rotating in this case clockwise and other half is rotating anti-clockwise. So net rotation is 0. Net rotation is 0. So rotation is mutually cancelled. But here because it is done by one molecule only, so here it is because of internal compensation. So this is optically inactive, but due to what? Due to internal compensation. So here now one thing more I will tell you, student, that is, if you relate mesoform with the levoform, you imagine a mirror. So this is not the mirror image of this, and this is also not the mirror image of this. So this is optical isomer of tartric acid, but is not an enantiomer of this, and also not an enantiomer of this. So when an optical isomer is not an enantiomer, then those isomers are called diastereoisomers. So these two are diastereo. These two are diastereoisomer. So here I am summarizing it for tartric acid. Tartric acid has 4 optical isomers. First is D-tartric, second is L-tartric, and third is DL-tartric acid, and fourth is meso. tartric acid. D-tartric acid is optically active. This is also optically active. This is optically inactive. This is also optically inactive. This is optically inactive, both of them. Mutual cancellation of rotation. Both cases, the rotation is cancelled. In this case, this cancellation is because of external compensation, and in this case the cancellation is because of internal compensation. So this is optically inactive due to mutual cancellation of rotation because of external compensation. Mesotartric acid is optically inactive due to mutual cancellation of rotation because of internal compensation. And these two are enantiomers, and this and this, these two are, and these two are. Okay, this is A and this is your B. This is B and this. These two. Meso, B is your meso and levo. And A is meso and dextro. Both of them, this is your diastereo isomer. This is also diastereo isomer. And isomerism is called diastereoisomerism. So here ends your isomerism. So next topic I will start, that is elements present in organic compound, that is detection of the element qualitatively, qualitatively detection of the element in organic compound. So till then, bye.